There's 4 antennas, and they're made out of RFI. It's RF Industries, an Australian company that manufactures radio antennas.
So these have been recovered and repurposed, or
yes, they are. Yep. They're no longer of commercial use, and they're model SMD 4-67. Current price is $450 plus GST for each one of these.
To buy them new.
To buy them new.
Yeah.
So we don't want to break them. They've got quite a robust plastic clamshell case here that protects everything from the elements, and you'll probably notice a couple of holes. There's a hole in the bottom of the plastic and a hole in the bottom of the folded dipole tube itself, which incidentally is aluminium. And that's the reason for that is should any moisture get in here because of condensation, it's got a place to run out. So there's 4 of these. There's 2 of them arranged as a pair,
so
3 meters apart.
So there's a pair. How far? Yeah. So how far apart are the?
Centre to centre is 3/4 of a wavelength, which is approximately 470 millimeters.
Right. Yeah.
Okay.
And then there's a 3 meter gap.
Yep.
And then another pair.
That's correct.
Right. And then the top pair will obviously have a harness.
Yeah, a combining harness.
A combining harness.
Other people call them a phasing harness.
Yep.
It's made out of a different impedance coaxial cable that matches the 50 ohm characteristic impedance of the antenna to a 50 ohm feeder cable that ultimately goes down to the repeater itself.
Yeah. So we'll get an opportunity to have a look at the mast and the harness and the feeder cables as we assemble that and go through the process of putting it into the air, basically. Yeah.
And of course the reason for having 2 pairs of antennas, if you pair 2 antennas up, you actually essentially double the performance of the antenna over one. So in the industry, doubling of the power, as you know, Paul, is 3 dB.
That's right.
So that 3 dB is taken into the equation of our licensed power output as well.
Yeah.
Which if we convert it to EIRP, we're looking at approximately 5.12 dB over an isotropic radiator, which is an imaginary aerial in free space.
That's right. But the biggest gain of combining aerials like this is on the receive side.
That's correct.
You're able to suck more RF out of the environment and feed it to the receiver.
Yep.
Yeah.
So the repeater actually essentially has, in layman's terms, a little bit more coverage. And going further, 6 dB, which is 4 times the signal, essentially equates to double your distance. So if we're only doing 3 dB, we're probably only doing about another 25% on what you do with a single antenna. Still better than nothing.
Well, everything that you can do to make things move in your favour is obviously going to be an advantage.
Yes, quite right. And the other advantage of these antennas is that they're relatively low profile. They're very lightweight because they're made out of aluminium.
Yeah.
And they are of commercial industrial quality that are designed to be covered in ice and snow. So we're actually averaging about 19 dB return loss. If we actually change the format to VSWR and change the scale, for those that like to work in SWR or VSWR, there it is there. It's at about averaging 1.2 to 1 VSWR, which isn't too bad. It's not.
So we're actually looking over quite a bandwidth here too.
Oh yeah, that's 400 to 550 megs.
400 to 5. So it's 150 megs bandwidth.
Yep.
Yeah.
It's pretty flat.
Yeah.
Okay. Just for the sake of it, we'll also. In fact, what we'll do is we'll just short that one out and see if that makes any difference to the other antenna. Just a tiny little bit. So if we put this on the other antenna, the top one, because that was the receive one we've just done, we'll just put LMR 400 on that. So we'll check the transmit one. It's not as good, but I'm not going to complain at 1.2 1.22, 1.23 to 1.
That's pretty good.
So its return loss will be about 22 dB return loss. Can't complain at that. So that's the VNA. That will also give us a Smith chart. In there is our matching, but you can see our impedance there.
58.6.
Yeah, so that's our transmit at the moment. And this is our receive aerial with the LMR 400 on it now. It was a slightly better match from my recollection before. 51.9 ohms.
Yeah.
Okay, so there we are. The Marconi is telling us that we're actually approximately 59 dB. It's a little bit more stable than the VNA.
We were neg 10.
Yeah, neg 10 first.
Neg
so
69.
Take 10 off that, so it's actually 59.
59, yeah.
Yeah, so okay, there's a discrepancy between the two, but I'm not going to worry about that. It's whichever instrument you believe, the Marconi or the VNA.
But you got better than 50 dB.
Oh, better than 50. Yeah, brilliant.
Yep. And of course, these are the kind of things, these are the kind of tests you really need to do before you charge up onto a hilltop and start deploying something. So you need to know where you're starting from.
Yep.
Yeah.
You see the ripples there? That's a car going down the road.
Yeah.
So it's amazing. You know, you could actually erect your antennas near a roof, maybe or metallic object as big as a roof of a building, perhaps, and that would actually grossly affect your isolation.
All right. Well, the next thing probably is to have a chat to Wayne and look at the physical arrangement that he's going to put in place to erect the mast at the top of the hill. But if we rig this in the final installation 3 meters between these two inner dipoles, we'll end up with slightly more separation.
Yeah, but from a practical standpoint, is that going to be an advantage? It's solely up to you. There's no disadvantage in it, but that's fine. I was just a bit concerned that it might be getting close to the roof structure of the property or something like that. I know there's not much in it, but it's up to you.
So what was that measurement again from there?
2.5.
2.5.
You take that again. So the two inner dipoles are 2.5
centre to centre. In fact, that separation is less critical than this one.
That's correct, yeah. The 470 is 3/4 of a wavelength at the frequency of the PRS channel.
Yeah.
And that gives us a good compromise with respect to gain and performance of the antennas.
Yeah. Yeah.
So they've been taped up now permanently with waterproof self-amalgamating tape. This one's actually been taped and masticed. This is the phasing harness, and this is the central point of the phasing harness. Here's the connector that connects to the coax that runs down to this repeater from the mast. That longer length is RG213, which is 50 ohm impedance coax cable. It's got an N socket at the bottom of it, which connects to the feeder, and then it is actually teed together at this point to a pair of quarter wavelength 75 ohm UR57 cables of the same diameter, and those are actually cut to their characteristic quarter waves with respect to the velocity factor and frequency that we use, velocity factor of the actual cable and the frequencies that we're using. These ones I've used the screw-on connectors, and in there, at the point that these are all combined, all the outer braids are soldered together and all the inner conductors are connected together. It's a little bit difficult to see in there, but the little combiner piece in the middle is actually made out of a piece of copper sheet that's bent up on an angle, and you can actually see it there, how it's been bent up and folded over, and I'll make an opposite cap on the other side and just fold the sides over and solder it all using a very, very hot old school plumber's soldering iron. I actually solder it all together. Firstly, I use a scope iron to tack the braids in. So there we are there. There's a close-up view.